Hello.
Hi, how's it going?
Hi, good. All right. We did two questions last time, right?
Sounds about right.
Yeah. Just to confirm, you are interviewing for Waymo?
Actually, right now Google, and now it's Fuchsia at Google.
Sorry, what at Google?
Fuchsia, it's a project operating
Oh, the OS.
system. Yeah, yeah.
I see. Okay, cool. All right. I believe the last time you did really well. I'm looking at the previous
Thanks.
feedback, and yeah. So today I have question for you. Would you like to do something? Do you have a specific type that you want to try? We did
Hmm.
what did we do last time?
I'm afraid I don't remember.
Yes, we did the kth smallest element from two
Hmm.
arrays, and
Okay.
then we did whether your car can pass through traffic cones.
Sure. Yeah, I remember that one. Okay.
Okay.
Mhm.
So any type like dynamic programming or graph trees.
Um, Anything really. Graphs are always fun, but like basically anything. Just sort of mix it up, I guess.
Okay, let's try this one um, and see how it goes.
Yeah.
Okay, so let's say you have a website that
Hmm.
allows users to find the 10 nearest restaurants to their location.
Okay.
Okay.
Hmm.
Today we're going to implement the backend piece that powers this.
Hmm.
So, given a list of 100 million restaurants, write a function that takes a user's location
Hmm.
and returns the 10 nearest. Okay. So for the
Hmm.
purpose of this question, 100 million would be n, and 10 would be k.
Hmm. Okay. Cool. That makes sense. And how are we representing these restaurants? Do they have like some just unique identifier, plus a location?
Right now, they are just coordinates. Um, Restaurants are x and y's, and x and y are bounded by -1 and 1.
Cool. Interesting. Okay. Um, I see. Okay.
What
And then
language are we
obviously,
using?
probably Rust, if that's okay.
Okay. All right. Rust.
Mhm. So I guess really this is location. This restaurant is a location, and the other input is just the user sort of location. Um,
Hmm.
right, 100 million restaurants. We'll find the K nearest restaurants. Um, sure. This, I think. So if we kind of abstract away the details of this being restaurants and locations and like Euclidean distance, um,
Yes.
the basic concept is we want the 10 smallest values from 100 million values. Hmm. Roughly. I mean, the really we're going to take differences between the user location and the restaurant location, but
Hmm.
we'll call that like the restaurant's like value. Basically, it's the thing we're ordering by, and
Sure.
to find the 10 smallest, we could sort the whole thing. I mean, it's a pretty big thing to sort, so we could do so naive. Well, I'll say sort. Um, so like approaches. We could sort. We'll take n log n time to sort it, and then just grab the first k things. I'm guessing in general, though, we're expecting k to be rather small, um, so it would be preferable to do something like a left-to-right scan with a heap of size or a priority queue of size k,
Okay.
and then we could get it down to the log k factor, and the memory also. Yeah, I mean, depending on if this is in place, you need some extra memory up to like so then memory. Whereas here you can just say, oh, k memory. So all in all, I think the heap is a lot more favorable just in terms of performance. And that way also you can write it streaming. So even if n was like larger than 100 million and didn't fit in memory or something, you could sort of also do something that took like disk I/O or network I/O and adapt this code to run that way.
Do you think that it can't fit in memory?
In this case, we're fine. 100 megs is not so much memory, or some factor of that, but it's a fair bit of memory. So it depends on sort of. I mean, most devices this will fit in memory is the short answer, but it's large-ish. And yeah, so this is an approach I like. I get the feeling there's maybe something like more. No, yeah, this sounds good because there's this like clever quick select thing which I've never quite looked into in detail, but that I think applies to getting some single element with rank k. And if we try to get the 10 smallest, it won't actually help us because we'd have to run it k times. So yeah. Anyways, this heap thing I think is pretty promising. Do you want to go with this?
Yes. So this is a good solution, NLK. But I'd like to ask you. Suppose you're in Tokyo and you're looking for 10 years restaurants. Would you consider? Would you bother checking the distance between you and some restaurant in London?
Probably not. Probably not. So you're saying that heuristically we can kind of maybe do better. Like in some sense by filtering, like we have 100 million restaurants, is quite a lot. So what am I trying to say? Basically, heuristically, we could guess at sort of a threshold and look only. Well, I guess interesting. So if we're sorry, one second. If we're thinking about this in terms of designing a system that lasts a long time, we might have some better ways to represent this list of 100 million restaurants.
That's correct.
And then we could take advantage of that. Nothing springs to mind as far as how to do that, but we can kind of explore that if you're interested.
Yes, because you have to understand that you only get the user's location during query time, but your 100 million restaurants, they don't change between queries. Right. Well, at least they don't change much.
Yeah. Okay, that is astute. So, but it's inherently sort of two-dimensional. Is the tricky thing about this data. So it's not clear. Like it would be nice to sort of group it, maybe literally just by sort of quadrant. Like I don't know what the granularity is here, but like by sort of like some like tile, because these are presumably on the globe, like on the Earth, and we'll pick some reasonable size of tile that is like the nearest. I don't know, like this nearest like metropolitan area or something like.
Okay, so you're talking about something like a grid.
Yeah, that's what I'm thinking of. Yeah.
Okay, so you are correct to say that the granularity is a problem because regardless of what you pick, you will end up with some parts of the world with too many empty tiles, like in the Pacific Ocean.
Yes.
And you have some tiles that are too saturated, like around Manhattan.
Sure. This is true. So perhaps there's a way to do this differently, although it's not clear what it is. I think you had mentioned this data structure to me actually last time, although I didn't look into it. There's some way to do like sort of this two-dimensional binary tree, like binary search tree like thing.
In the past?
I think so. At the very end of our interview, when we were talking about a car driving through pylons or something, you said, well, actually, there's this data structure. And I didn't look into it, but it seems like it would be very relevant here.
The same data structure can be used for both questions. That's correct. So for the car driving one, this is more of an optimization. But for this question, that data structure is very core.
Yeah, unfortunately, I don't actually know anything about the data structure besides the fact that it's intuitively sort of sorting by these two dimensions and achieving like logarithmic lookups.
Okay.
I guess actually, come to think of it, this must be how databases, I know nothing about databases, but they store like composite indices over like a pair of keys, right? and they must use something
Hmm.
like this. Does that seem reasonable?
It's
Like, so
basically
yeah.
a binary search tree with
Mhm.
more than one dimension.
Mhm.
So
Okay.
in a binary search tree, at every node you either go left or right, with a smaller or bigger, right?
Mhm. Mhm.
But if you have two dimensions, then you have four ways to go.
Sure. Sure. And we could say like
And if
left
you
and
have
right
three
is this
dimensions,
x, and like up and down, let's say, is y. But my question is, how is this different from storing a single binary search tree that is indexed by the x key, like keyed by x, and then a separate binary search tree that is keyed by y? Like, where, obviously that's not exactly what we're doing, or maybe it is.
well, if you do that, then you're gonna have to end up with a cross cross shaped search space. So okay, I'm in drawing
Hmm.
mode right now.
Sure.
If you have a if, this is the world, right? This is the world. Your first binary search tree, if it's by X, it's gonna look like that. Uh you're gonna have something on the left, and then you have something on the right, right? And then
Hmm.
you would have, and within this you're gonna have another two sections like that, and like that. Okay, and then you have a different binary search tree for the Y. So you're gonna have Y like that. Are you seeing what I'm
Hmm.
drawing?
I'm not fully understanding it, honestly, but yeah.
So if you have two binary search trees, and you find and you are able to find where the user is in one of the binary search trees, and
Hmm.
where the user is in the other binary search tree, you end up with a cross shaped region where you need to process.
Hmm.
Okay,
Whoa.
so previously you mentioned, so I'm gonna move this aside.
Hmm.
Previously you mentioned that you want to do a grid. So a grid is like this, and the most elementary grid you can have is a two by two, right?
Sure.
Yeah. So here you have a two by two grid,
Um,
and if one cell is oversaturated, what can you do to it?
um, let me think about that. So if cell is oversaturated, you can let me let's say like this cell is much heavier than this one and this one. Then well, on like a binary search tree that's just like the left-right split, you would rebalance to sort of in some sense push some of the mass over to the right. But you actually have
That's
options. You can
Yeah.
also sort of
That's one
rebalance
way.
across this
You
axis.
can move your line to the left, right? You can move the line like this.
Yeah, I see what you're saying. I see. Yeah, yeah.
Okay, but that's not what I want to get to. You can repeat this process basically.
Oh, I see. I see. Cut it. Sure. Okay. Okay. Interesting. So, wow, interesting. Okay, so you're saying you subdivide it further, but quick question: is it self-balancing in any way or not? Like, there's no
It's not. In
rotations.
fact,
Uh,
if the data is random,
mhm.
it will not be self-balancing. In
Yeah.
fact, well, there are very many variants, but the one I'm describing right now, it has
Mhm.
fixed coordinates. So you are
Mhm.
dividing them into four equal squares, and you're subdividing them into four squares all the time.
Mhm.
So parts that are more dense, it's just going to be deeper,
Okay.
and that's fine. If you want to self-balance it, you're going to end up with a slightly more complicated way of representing them, which may have some advantages depending on use case. It's up to you to explore. But I don't think there is enough time in an
Yeah.
interview to do that kind of exploration.
Totally. Yeah. Okay, so this is starting to come together and make some sense to me. Like, and in some sense, this dynamically captures this like grade granularity problem by saying Manhattan, which is very dense, is going to end up getting split, 100 times
Yes,
and so
correct.
on.
Yeah,
Whereas, yeah,
but
in
this data
Target is,
structure can be defeated by an adversarial data
hmm,
input, right?
okay.
If pi is equal to uh, 0.5 of pi plus I minus 1, then you're gonna have you're gonna have a very heavy tail, and each cell will, you know what I mean?
Not quite. So P, these are the point coordinates, right? And this is
Yes.
like say X, Y, the
Yep.
horizontal coordinate. And you're saying so you keep cutting magnitudes in half. So in particular, it's like a point here, and then a point halfway, and then a point a quarter, eighth, so on, and you're converging down to like approaching zero, say, or
Yes.
maybe you're doing it diagonally
Then
this way or something.
yes. Then your tree, your
Yeah, you
recursion
get linear
tree.
depth. You're saying you're going to fool this into
That's
being a
correct.
linked list. Okay,
That's correct.
I see. Okay, word. Right. But I guess in practice, the data probably won't look quite like that. For restaurants, for example, they're not going to adversarially decide where to open up, pizza places in Manhattan.
Yes.
Cool. Okay, so I have a very high level kind of grasp of the idea. Do we hope
Okay. So
to?
suppose
Mhm, mhm.
suppose your data is already in this data structure. How would you use it
Hmm.
to find tenuous?
Yes. So the data structure is somehow representing basically these cells. I haven't yet decided how, but it's going to tell you sort of. I mean, I guess in some sense, there's one top level node, which is this like big rectangle, like this is
Mm-hmm.
the largest outer square, and then there will be um, either, I guess there's two flavors of nodes. There's a node that's like a leaf node, and on a really sparse data set with like one element or something, maybe the whole tree is just one big leaf node. But otherwise, interior nodes have four children, as we pointed out, like these sort of four quadrants. Um,
Mm-hmm.
and in each of those four nodes, again, we'll have the pattern of it being either a leaf node or divided in four.
Yep.
And as long as we sort of, I mean, I'm not going to worry too much about things that are exactly on the boundary. We'll just sort of round them one way or the other. And I mean, it might be subtle to worry about that for correctness of the implementation, but it also might not, because a lot of the times, things just sort of work out. I don't know if that's convincing, but anyway, so I'm not going to worry like too hard about the lines that, like points that lie exactly on one of these
Okay.
lines for now. All that to say is that when you have a point, if the current, like let's say you're finding a point, you're putting like the find routine. If the current square, how do I say, is a leaf, then the point should be in that current square. Otherwise,
Mm-hmm.
you figure is the point, and let's suppose we're also tracking the current ranges of x and y, which are 0, 1, 0, 1, the whole axes to start with.
Mm-hmm.
Then, yeah, you find, does the point x lie on the left half or the right half? So it's sort of like a binary search. And then you do the same thing for the y as well before recursing. And then you'll end up with a quadrant because there's sort of four ways that could be. It's like x minus, x plus, and y minus, y plus, let's say. And,
Okay.
or however yeah. And right, and that'll select you a quadrant. So you can recurse on that quadrant and record the fact that your new sort of frame of reference is this smaller box. And your point lies inside it, so you just keep recursing basically until you find a leaf, like an inner indivisible box that contains your point. So that's like a
Okay.
lookup of a point.
Okay.
Right. So the question is though, what do we actually want? We're trying to find something a little different here, which is like, in particular, pretty different. This section I want. Try to see this. Okay. Yeah. Questions of Canadian restaurants. Yeah, this is interesting. So we could, well, I don't know if this is cheating, but if we augment the existing data structure to include a count of the number of things it maintains, not just for the whole data structure, but at every node. So this
Okay.
entire
You definitely
square,
can do that.
okay, nice. That'll help a lot. So this entire square will have like, let's say 100 million is the count. And when we figure, we're looking, let's say that the target that we're searching for is the user's location. We want to find their exact location in the data structure for now.
Mm-hmm.
And that would put us squarely, let's say, in this top left coordinate, top left box. And as long as that top left box has at least 10 restaurants in it, we can throw out everything else and just not worry about it. So we're now on a much smaller problem. And by doing that pretty quickly, we'll converge to a very small problem. But the around the edge cases where we start to hone in on, on tiles that are leafs but only have let's say 5 elements in them, because at that point we've sort of gone too far, if that makes sense. So
That's not necessarily true.
well, maybe if we can go back up, like if there's parent pointers of the nodes, and we can sort of, yeah, I guess, well, yeah. So
You should conceivably have this problem, right?
well, I guess I have a meta question about the guarantees, or like the invariance of the data structure. Is there like a maximum and a minimum number of elements for a given leaf tile? Do you understand my question? Like, is that a guarantee? Yeah.
I see. So yes, physically there should be a minimum. I mean, if you map this to the real world, restaurants, you can't conceivably have more than 100 restaurants with practically the same X and Y coordinate. You can have that in a multi-story building, but yes, you're right. There is a realistic limit. So let's assume that there is such a limit. But what are you going to do with this information?
That there is a limit. Well, so I'm hoping for something kind of like there's some factor, let's say like B, which is I don't know, 100 or something, and I'm hoping that each leaf tile contains between B and B over 2 elements, or B and 2B elements, something vaguely like this, some sort of bound that.
Oh, I see. No, you can't,
no.
because like I said, the oceans will have 0 and Manhattan will have a lot.
That is true, but how do I say? We don't subdivide the oceans. Like this bottom left quadrant maybe is like the whole Pacific Ocean roughly, or at least I mean, maybe we don't have quite this guarantee, but at least an upper bound would be nice to say that so the data structure was not filled in by bad code that has 400,000 in a single leaf. That would be really awkward.
Oh, that would actually happen. So you see, so suppose there are some small islands here. That's why there are 2 restaurants and a bigger island here. But let's say this is the tip of a continent, I don't know, Cape Town in South Africa or something like that. And this would still be 0 and 0, and this could be 200,000.
Right, but if it were 200,000, you'd hope to divide it further until eventually
Yes,
it's
correct.
100.
So these two will be divided further, and these two will be divided further, but you still have a lot of zeros here.
Right. And I guess, okay, interestingly, one point you're getting at, so I'm starting to clue in that the thing I was thinking of is too naive, I think. The thing I was saying, well, let's find the user's location and ignore. I was hoping that it would be safe to, as we drill into this 400K, since there's so many in this quadrant, I was hoping it would be safe for us to ignore this 2 and the 7. But as you, I think, are alluding to, potentially, actually, that would be unsafe, because our user's location might be kind of on the edge here, and it's actually quite close. Right. So
that's correct.
So that adds complexity.
So yes, but I want to prevent you from getting lost here.
Okay, sure.
There are 2 cases, right? There's one case where you find the leaf node that your user is in, and your 10 nearest restaurants are in there. That's the happy case. And there's an unhappy case where there are closer restaurants that are outside the square that you need to deal with. Okay, so let's focus on the happy case, and then we'll go back and think about how we deal with this unhappy case. Okay.
Okay.
Okay. So based on how you described the data structure, it sounds like there's a guarantee that each cell, each square, will have between 0 and P number of restaurants. where
sounds good.
C is the point at which you decide that a cell has too many and you're going to break it up into 4.
Yeah, sure. Sounds good.
Right. So what do you think C should be?
That is a great question. I mean, maybe like 4,000, just off the top of my head. That's a reasonable number.
That's a very good guess, by the way.
Okay, thank you.
Yeah, it is. I don't know the answer, so I wrote the code and ran a random simulation. So for random distributions, 10,000 is a good number.
Oh, nice. Okay, cool.
Yes. And the reason is because why do you think 10,000 is a good number?
Um, well, I'm guessing each of the leaf tiles is its own like allocation. So it's like when you're implementing a binary tree, let's say, you don't want to have the data like fully just scattered across memory addresses and completely like no locality at all. So making it basically nice and big is good for memory locality, to be able to like read like a sort of sequential or closely packed pieces of memory. But also if you make it too big, then you have to read the whole like 10,000 or 20,000 sort of elements left to right. And so that's like, these are the two sort of contending trade-offs, I think, roughly.
That is very good observation. But more related to this problem, it's actually that there is not much performance gain doing n log k, where n is 1,000 versus n is 10,000. And in fact, it's very expensive to do n equals 10 or n equals 100, because there is setup time to, for a function call or to do and you're setting up your heap, right? Your priority queue. So at 10,000, it's a good balance, where there is enough data and the computer can process 10,000 very quickly. But if you go beyond 10,000, then that is the linear part of the problem, right?
Yeah,
and it gets bad. So 10,000 is a good number. And the other thing is, what do you think is the probability of being in the happy case versus the sad case, depending on C?
I guess, when C is large, it makes it extremely likely that you're in the happy case. So that's something I hadn't thought about, but that's probably quite relevant here. Because imagining, you're in some kind of tile which is aligned to these like boundaries. It's and you have 10,000 things in it. It's extremely unlikely that you just so happen to be at the very edge of the tile and like there's some closer things that are actually here.
Yep.
Yeah, I guess intuitively. Yeah.
Okay, let's assume you have this data structure already done. I want you to write the function, so find 10 nearest or find k nearest, and let's work on the happy case, and then we can talk about the unhappy case.
Okay, I will try. So let's think here. So find k nearest, and then you have these sort of data structure. I mean, there's a name for this. What is the data structure called?
Quad tree.
Quad tree. Okay.
So it's a quad node.
Okay. Reasonable. Yeah. Let's see. Quad node. So quad node. And then sort of target data points. Okay. Points. So, right, and in the quad node, we said we had sort of like num points.
Okay.
And, how do I say this? There's like there's two types here. Yeah, it's for the children. I guess, how do I say this? There's like a leaf. I'll make this first, say quad leaf is one type, which has no children, but it does have
restaurants.
restaurants.
Or content.
Yeah. Let's say points is an allocation of some number of points. I guess it's a specific number, like points, optional points, and there's some number of them, like 10,000. So something like this, I think. Actually, sorry, this is a weird data structure, but like basically we want a list backed by an array. So I'm sure there's a library for this, but anyways, yeah, list of points.
Okay.
And sort of a quad branch or something. Like this other node is going to have children. It's going to have exactly 4. I'll call them like top left or something like that. Quad node, where quad node is like basically is a leaf or a branch. Leaf, branch. So, and then, yeah, you have 4 of these. Top left, top right, top left, top right, let's say.
Okay.
And then the whole quad tree is like, I guess it's also a quad node. Yeah. Okay. Seems reasonable. Yeah. Okay. So I think, well, so num points. We actually care to know the num points in a branch as well. I don't know.
Num points would just be the size of the vector in quad leaf, right?
That is true, actually. Yeah. Yeah, it's redundant here, but not here. So like total num points or something like that. Yeah. Yeah. Okay. Cool. I'm pretty pleased with this. Question is, how do we use it? So there's sort of 2 cases basically. Self, if it is a quad node leaf, what do we do with it? In the other case, what I actually want here, I want leaf, quad leaf, points, and then basically insert points when at least k. And there's actually another check we have to do here. It's not as simple as this. So I'm not sure how we just to do detect, now detect if we're in the happy case. I'm not sure how to do that, but anyways, yeah. And then we just want to return the points that are closest to the target. So we can do that via a subroutine. The nearest of points. We need like a ref somewhere here. I'm not sure, but we need to take points by reference. I'm not sure what the syntax for that is. So basically, points should be need points, we need k, and we need target. So let's do that. And then this will return a value, and we can just directly return that. So I'll write the helper function. So this is the heap thing we were talking about before, basically, I think. Well, honestly, if it's small enough, yeah, let's still use the heap. I think that makes sense.
That makes sense. Yes.
Again, here search points when we're let's, and so we want heap. I guess it's called heap nearest, and I want the first, or I could just make an empty heap. Let's think about this.
Are you making a max heap or a min heap?
That is a good question. I've done something like this before, and I remember it's not the intuitive thing. So we want to find small elements, and to find small elements, we'd like a max heap so that we can kick out the larger candidates that are less useful to us intuitively. Yep.
Good.
So, and a max heap in Rust is a binary heap, which is max by default. So we can create a new heap. I want to at least have it with capacity, say k plus 1. Yeah, I'll do it like this. This is that nearest. And at the end, we'll just flatten it into a vector. But the sort of main loop here, like for key points, I'm going to, what I'll do is I'll push the point to the heap and then pop the largest.
Okay.
I don't know if that's the clearest way to write the code, but that's, I think I'll try. So basically push P, except for keyed by some, I'll come back to this to do order. And then there's pop. Well, so if nearest len greater than k, search equals nearest one pop. This is the flavor of what I'm trying to do here. The thing that's missing, I think the only thing that's missing is the ordering on points, and that ordering is it's this distance property. So it would be kind of nice if points were actually a data type, so we could find methods on them. So, I'm going to change this from being an alias to actually like a real proper data type. So like y we said. The full point we'll be able to do like say norm, which is like the Euclidean norm, maybe I'll call it.
Okay.
Which is like how do I say? So we have point self copy in quotes, and it's we literally just want square root of the squares. So say so self x over 2. Not really sure what this method is called. Something like this. Self y to vertical thing. I think that's all we have to do there. And then we want subtraction for points. So we can take a difference, which is impl sub for points. I think, then type output. So output points, sub, self, and yeah, so x, so self x minus other x. Y self minus other, sure. Just that. And then yeah, so then now I think we have enough to be able to compute like distance between 2 points, which I guess could be a function here, like function distance, self other, which is like the say other than self dot this.
That is a very interesting way of calculating distance. I've never seen this, but yeah, this is correct.
Okay, yeah, maybe I'm overthinking it. It just felt natural to have subtraction. Yeah, I don't know.
Yes, typically we would do the Pythagorean theorem. You just take the x, take the difference in the x and the difference in the y, you square it.
Yeah.
And for specifically for this question, you don't need the square root because you just care about the ordering. You don't care exactly.
Oh, neat.
How it is.
True. Cool.
And you save a little bit of computation on the square part.
Okay. Great. See that? Nice. Right. So this is okay. So cool. But now I have to somehow get this to work with my binary heap. So let's think about that. Yeah. I'm going to do something a little hacky and say that points are ordered, even though they shouldn't be, so that I can have the elements of the heap be like two things, be like some sort of distance, and then the points.
Okay.
Again, this is not what you should do sort of in practice because it doesn't make sense for points to be ordered, I think, but I'm going to do it anyways. So the question is, what is the distance we care about here? It's target distance p. And then that's what you're pushing with, and they're going to be popping, yeah, this, I guess, is all we need. So wait, well, so max heap, max by distance. Yeah, cool. Okay, and this is pick out the points with largest distance. Cool. Yeah, so I think this is basically what we wanted there.
Okay. So I'm not familiar with Rust, so I don't know what you mentioned about how points should not be ordered, that particular argument.
Yeah, I can speak to that. Like
Because
basically,
you're not ordering points, you're ordering tuples, right?
yes,
Right now?
yes, yeah. The issue though is that for this pair of values, so the type, I'll like write the type here, which is that it's a binary heap of f64 comma point. And for this pair, this tuple f64 points to have to implement the like order trait ord, you need the point to implement ord. So the hack where I implemented it on point was to allow me to write this. What you probably should do instead in production is define a data type like heap element, which has the distance and the points, and then you'd implement ordering directly on heap elements. And the ordering would look like ordering by distance and ignoring the point. And that way I can leave.
Okay, good.
Yeah,
awesome.
Yeah.
Thanks for explaining.
Yeah, no problem.
This is great. Okay. So one thing about your implementation of of indiscriminately pushing things in and then popping them out, that means that this is C log K, right? C is the capacity of the cell. So you have C of them. By doing this, you are forcing heap reordering for all C of them.
That is a good point. Yeah, that's pretty rough, actually. Okay, true. The constants are not that good. I agree.
So if you compare, before you push it in, you compare with the biggest element in your heap, and you only push it in if it's smaller, then you will save on heap reordering.
Yes, yeah. In particular, I'm not sure how to phrase this, but like the average case, you save a lot because unless the input is like reverse sorted or something adversarial, the usual operation is just to peek and then decide you don't care and you don't mutate the heap at all, which is O at 1, which is much better. Yeah. Okay. Cool.
Okay, but it doesn't change the time complexity, so I'm going to let it go. Okay.
Okay.
So now that you have done this, you have found your 10 errors. Okay, now time to move on to the unhappy case.
Okay. Great question. Well, we also need to do this like recursion somehow, but this is just the sort of bisecting thing we mentioned, right?
Where are you? Are you in the drawing?
I'm on line 59. I did not implement the case to recurse on a subnode when we're not yet at a leaf.
Okay, but that's pretty trivial, right?
Yeah, I'm sure we could do it. I'm interested to think about this unhappy case because I don't yet have any really solid ideas on how to do it. I think like one concept that seems reasonable, but I don't yet see it working is like going up somehow, like or at least checking like neighbors in this vague sort of sense. Like we have. Nice. I guess we could probably detect. Yeah, we can detect if we're in the happy case in a way that like usually we will correctly detect like there might be some false positives and we'll say, okay, we can't verify that we're in the happy case, so let's do the heavy lifting. What I mean by that is
how do you verify that you're in the happy case?
Yeah, the quick check we can do is just say how do I say it? The point, the target within its bounding box, its distance from any edge is greater than the farthest of these 10 points that I currently have. Because that means to me that like I do not have to go outside the box, because everything outside the box is actually strictly worse than what I've already got.
Mm-hmm.
But if we're
Good.
really close to the edge, then we can't be so sure
Okay.
to any edge.
That is
Yeah.
absolutely right. And the other case is that, so over here, I wouldn't do the assert that it has more than or equal to k.
Mm-hmm.
I would just find, up to k nearest, and then you check if you have 10. If you don't have 10, then you also need to look out.
Also true. Yes. Yes. Good call. Good call. The question then is, what do we do about it? I guess intuitively, like supposing you're really close to the left edge, the bounding box, you just want to kind of find the thing to the left of us geometrically, which potentially involves like going up for a while, maybe, because if we're in this like deeply nested sort of structure, we might not actually physically go to the left until we've gone to our parent. Like, I guess we can go up to our parent, and then if we see that we were one of the left children of our parent, we keep going up, and then until eventually we get to a node which was on the right half of its parent, then that parent is the sort of shared ancestor. I should draw this, but like the shared ancestor of these two. This is what I'm picturing here. It's these two which are cut by this edge. I don't know if this makes sense, and this is only to try to implement the functionality of going physically to the left.
Yes. What you're describing, I can clarify it for you so that it's
sure.
clear.
Yes.
What you're trying to do is you're trying to ask which nodes overlap with my circle, where the radius is defined by distance.
Yeah, that's even better, because we might also have to go down as well as left, like if we're near a corner or something. Yeah.
So
but we won't always have to go in all four directions, right? Like you can probably say something about.
Yeah, you don't always have to. So using what I described, you could ask the root node, or you can start from the root node again and say, which nodes overlap with this circle.
Oh, cool. I see. And is that okay? That's cool. I like that. And is that a query that's?
But the problem is, you might overlap with some really dense squares,
right.
and you end up with too many points. So you want to binary search a good radius.
Oh wow. Huh. That's interesting. Huh. Binary search a good radius. Yeah. Wow. Huh.
So after you binary search a good radius, you end up with a bunch of nodes that overlap that circle with that radius, and then you repeat whatever you're done with k nearest, but this time with all the overlap nodes, and you will have your answer.
Okay, got it. Interesting. Is there any reason to instead do an approach where you're sort of physically just moving to the left from where you started? Like, is that something that has promise?
You can, but you may be in a big node, and if you move to your left, it might be a very dense node with lots of children. Then it's going to be complicated to figure out, which is your left node. You could have multiple nodes that are directly next to your left edge.
Also true as well. Yeah, actually, okay, yes, I can see this getting complex quickly. Okay, yes. Got it.
So conceptually, it sounds easier, but implementation-wise, it's going to end up being very similar to just finding nodes that overlap with the circle.
Gotcha. Yeah. Okay, cool. And how does one do that? Like, how do you search for a range of points essentially, or like a circle?
That's a geometric problem. So I wouldn't expect candidates to know how to do that, and you can search for that online. Here's a good one.
Sure.
I pasted that in the chat. You can see
it. I see. Let me find it. Gotcha. Okay, cool.
It's actually just a one-line equation.
Okay. I'll take a look after. I don't want to
Yeah.
keep you. But
Um,
cool.
but I think you did fantastic. Okay. And I
Oh,
want to
thanks.
say that this solution is not the best.
Ah, interesting.
The better solution. I, I, do you mind if I
Hmm.
spoil it for you, or do you
Oh
want to
no, go
figure it
for it.
out?
Go for it. Please do. I'm interested.
Okay. So the easiest solution is actually to have a quad tree with capacity
Hmm.
C at maybe 4 or 5.
Okay.
Okay. And what you do is you take the entire tree, you put it in a priority queue.
Hmm.
Okay. And then at
Oh,
every step,
wow.
you pop out the top element and you unpack it.
Hmm.
And the priority queue is ordered by distance. So if your priority queue can contain nodes or restaurants. So when you pop out a restaurant, it's one of the nearest restaurants. It's the nearest restaurant so far. If you pop out
Hmm.
a quad node, then um, it may contain restaurants or nodes. And how do you
Hmm.
order those nodes with restaurants? Well, with restaurants, it's just points, right? It's easy to order. You
Hmm.
just use the
Hmm.
formula. For a node, you would you would order them by the maximum distance.
The maximum.
The furthest point in that node to your user will be what
Interesting.
you
I would have
order.
thought it might have been the closest because you're trying to.
Yes, yes. Sorry,
Okay,
closest,
sure, sure.
correct.
No problem, no problem. Yeah, yeah. Got it, got it.
Yeah, closest.
Gotcha,
So
gotcha.
if you just repeat this process and you pop out 10 restaurants, 10,
Hmm.
you're done.
Fascinating. That is very conceptually clean, and it's like unlikely, I guess, to do a lot of extra work, probably. I mean, yeah, intuitively, you're doing exactly what you have to because those tiles could potentially have the things that you care about.
And because you know, based on your data num points, you know the number of
Hmm.
points in a cell, you could potentially prune. Sometimes you don't need to
Hmm.
push nodes back into the queue if you know that, I have enough things in my queue that that everything in this
Oh,
box
okay.
will never make it.
Okay.
Then you can optimize that way.
Interesting. Okay, that sounds a little subtle, but very reasonable. Huh. Neat.
Yeah.
Okay, very cool.
So
Well,
this solution, no one gets to it because I wouldn't even encourage it. It
hmm.
requires so much insight. In fact,
Hmm.
I've used this question for a good half a year before
Hmm.
it just came to my mind that I could do that.
Huh.
Um, yeah, this question has been asked. I asked more than 200 times in Google,
Wow. It seems like a
and
difficult question. Like, what level of candidates do you give this to?
I give this to level 3 to 5, and
Hmm.
the amount of guidance I provide would vary depending on the level.
Hmm. Yeah.
Um, I will say that you did one of the best. So
Oh, thank
I
you.
think I'm surprised that you're going for an entry level position.
Hmm. Yeah. I mean, I am a new grad, so I think I would struggle to convince them otherwise. But
I see, but you did great. I mean,
thank you.
so did I tell you the two things we care about
Hmm.
in a coding problem,
What are those?
which is coding and problem solving.
Hmm. Okay.
So
Makes sense.
for coding, it is basically how comfortable and how fluent you are in writing code, like how familiar you are with it, and
Hmm.
based on what you have typed,
Hmm.
the code you have written, it's amazing. You
Thank you.
are, some candidates they could write the find k nearest, and then they would talk about the struct, they would talk about the helper methods, but they don't implement it. But you
Hmm.
are able to go and implement those things really quickly while writing the main function.
Hmm.
Amazing. Okay, so your coding is
Awesome.
out of this world. You will
Nice.
get a strong high rating for your coding.
Wow.
The other
Okay.
thing is problem solving. So problem solving is process and being familiar with data structures and algorithms.
Hmm.
Again, amazing.
Hmm.
Okay. Most of my candidates, they don't figure out this data structure on their own. um, you had a tiny, tiny bit of hints from me to get to this
Hmm.
data structure, but
Hmm.
otherwise you have driven this solution largely on your own. Okay,
Hmm.
so definitely amazing on data structure end as well, on
Hmm.
problem solving as well. So
Hmm.
I don't have much feedback to give to you beyond this. I think you are
Okay.
completely ready to
Oh,
do your
wow.
interview, do amazing at it. Okay.
Awesome. Thanks.
Um,
Thanks.
Perhaps you want to try different kinds of problems to make sure that you have the same ability to solve those kinds of
Hmm.
problems. So actually, why don't we do this? We have 5 minutes. Do you want to
Sure.
try thinking about different problems?
Yeah, yeah, sure. I'd love to.
Okay.
Actually,
So
before
I'm
we do,
gonna.
I had one lingering question about the queue approach. You mentioned the tile size, like C should be small, like 5. Why make it so small?
Because you're pushing individual restaurants into the queue.
Right, right. Yeah, I guess heuristically, intuitively, it seems reasonable that it's sort of, yeah. Okay. I mean, yeah, it seems very plausible. I believe you. Okay, cool.
Okay. So this second question, it's
Mhm.
requires a bit more thinking.
Mhm.
So I'm gonna paste it at the bottom, and let's talk about it.
Okay.
Usually, I take about 10 minutes to explore this problem with the candidate before we even try to solve the problem, just to make sure that the candidate has a good understanding of what we're trying to solve.
Right. It
So
does seem pretty dense. Um,
yes,
bar rate sounds, and it sort of has a similar flavor in terms of division of geometric space. Um, do you have like a long background in this? Did you do like a PhD in these data structures or something, or have you worked with them for a long time?
no, I work in Google Maps.
Right. Okay. That makes sense. That makes sense. Um,
Well, I worked in Google Maps. I left Google half a year ago.
mhm.
I was there for 10 years.
That is quite a while. Can I ask why you left, out of curiosity?
Oh, Google likes to cancel products and
Ah,
reorg stuff.
yeah.
So I was working on a project for 2 years, and then they canceled it, and I have to find a new team. So
Mm.
if I have to find a new team, I told myself, okay, why not? I'll consider other companies as well. It's a new team, right?
Mm.
So
Yeah.
so I interviewed, and I realized how underpaid I was, so I
Oh,
left.
right. No, that does make sense. I think it's in tech broadly, like people that stay at one place for a long time get underpaid, and I think that really sucks. I mean, it's a bad incentive, but
Yes, it's
yeah.
it's crazy. My new compensation is 50% higher.
Wow. Yeah. And you couldn't just sort of negotiate with Google based on that, like the offer? I guess they would.
Um, I don't know, 50%. It made me
Right.
feel terrible. Like, okay, I
Yeah.
should have left 3 years ago.
Yeah. Yeah. Wow. Hmm. Right. Okay. So sorry, I'm like halfway through reading this. So we have these divisions into sort of zones, and we can squash the largest tile in a zone, I think, is what I got from the first paragraph. So,
Yes.
and we're choosing how to bifurcate. So every day we have to build one horizontal or vertical barrier. Cutting, cool. So,
In each zone.
oh, in each zone. Ah, okay. So it is sort of, I see, I see. Two zones, one zone, because only a single city block is contained. True. Okay. Ah, no sustained. And the damage, and so we're trying to optimize for this damage metric is basically the number of roaches alive, like the integral or something, like per day, the number of roaches alive until we eventually contain everything. Um,
Yep.
one
You
thing
don't actually kill the
hmm,
roaches. You're just
I
negating the
see.
damage done by
I see, I see, I see. You're sort of fighting them off or keeping them tied up. Okay. I see. Okay, yeah, because I was about to ask this. None of these numbers are going to zero, but I see. Okay, so eventually, I see, I see, I see. So we'll only, I mean, unless there's any like zero tiles in the input, we have to actually fully divide up the entire thing into this tic-tac-toe board to
yes.
to reach like a stable state. Would there ever be tiles with zero roaches?
Um, let's say no, but I don't think it
Okay.
matters.
Okay. Reasonable. Reasonable.
And here's an example.
Okay. minimum damage must be sustained. Okay. Yeah, so we're trying to optimize this, and I guess intuitively, so let's suppose we just didn't build any barriers, then like the maximum tile is the thing that we're currently like dealing with, and everything else we're getting damaged by.
That's correct.
And intuitively, heuristically, what we want to try to achieve with these divisions is to get other like maximal tiles or other quite large tiles and be able to squash or at least manage those as well. So that in our first example, that kind of explains why we cut 447 from 147, is so that we're able to handle both of them. And then it's not clear that a greedy thing will work, mind you, but like that's sort of a vague sense I have about how the things we're hoping to optimize. And then
Yeah. And I just pasted an example to show that greedy will not work.
I see. This is number 3?
Yes, 3 is the optimal, but if there are just 3 more roaches in the 29, then approach 2 will become the optimal.
Okay, I see. So you're saying, so approach 1 probably was the greedy thing. Okay, we're cutting 95 from 40, and then we're cutting, interesting. So I didn't miss this. This makes sense. So when we chose to cut 95 from 29 and 40 from 10, we actually had flexibility here. Like we partitioned zones individually, right? Like I could have cut, okay. Yeah, I don't know if I'm going to think of the optimal solution here. I might have to go and think on this, but this seems really interesting, and I will definitely spend some time with it afterwards.
All right.
Cool. Well, yeah. Again, so thank you so much for your time. These were really fun and interesting problems, and yeah, thank you.
Yes, I'm very happy and with how you did. Good luck, and yeah.
Okay.
Have a good interview.
Thanks so much. Yeah, maybe we'll meet again someday. Yeah. Cool. All right.
Okay.
Take care.
Yep. Email me your solution. I'll be happy to talk about it, and I can send you the write-up as well.
Oh, sure. Actually, yeah, sure. Well, so I'll let you know if I do attempt it, and I'll let you know. So I'll give you my email in the thing. Cool.
Yep. Okay. Bye-bye.
Good. All right. Ciao.
Yeah.